Hello and welcome to chapter 11 of Algebra 2. In this chapter, we are going to look at sequences and series and hopefully use that to your advantage to solve for something that is pretty important in the near future. So let's go ahead and start by defining each of the following then. In our first case, what I would like to do is introduce, or define what is a sequence. A sequence, we kind of like talked about it in the last section where it was more of a discovery. A sequence is, in short, kind of like a non-mathematical term, well, sort of non-mathematical terms, a list of numbers, generally a pattern, right? A list of number with generally like some sort of pattern. So for example, if you have something like say t of n, that's how we denote a sequence, is equal to maybe something like say 5 and then 7 and then 9 and then 11 and so on and so on and so on. So that is going to be our sequence, and you'll note that the pattern is, well, we start at 5 and we just add 2 to get to our next term. Another example of a sequence may be something like say t of n is equal to let's make it a little bit more difficult. How about if we make it like say 5 and then we have negative 7 and then we have 9 and then we have negative 11 and then we have 13 and then negative 15 and so on and so on and so on. So in this case, you can see what the pattern is. And writing an equation for that one probably will not be as easy as the first one. But nonetheless, it is a sequence. Now, to be a little bit more, I guess, mathematical about it, like in terms of algebra, we're going to define a sequence as the following. A sequence is basically a function where the domain is going to be the set of whole number set. A function where the domain is the whole number set. So you can think of it as this way. These numbers in the sequence, they're basically terms, right? This is going to be our first term. This is the second term. This is the third term. This is the fourth term. This is the fifth term. This is the sixth term. So in turn, this is like saying when n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, n is equal to 6, because we're just looking at each term, and because of that, well, we're just using whole numbers then. In the previous one, once again, we can go ahead and say a little bit more specifically, t's of 1 is equal to 5, t of 2, which is the second term, is equal to negative 7, t of 3, which is equal to 9, and then t of 4 is equal to negative 11, and so on and so on and so on. And when somebody writes t of n, that usually means what is the sequence as an equation. And if you can write that equation, great. But sometimes you just cannot do it. So to introduce the sequence to something simple, we're going to go ahead and look at two sequences where we can write the equation. Those are known as arithmetic sequence and also a geometric sequence. Now, for an arithmetic sequence, it's basically a sequence where you add consistently to get from one term to the next. So that's literally what we're talking about in the previous example. T of n is equal to 5, 7, 9, 11, and so on and so on. If you look carefully, you can literally come up with that equation because that's really just a linear equation. Now, to help you see what this linear equation is, maybe we can do the following then. We can say this. T of 1 is equal to 5. And I know this is a little tedious, but just to kind of bear with me for the time being. T of 2 is equal to, instead of 7, I'm going to write 5 plus 2. T of 3 is going to be equal to 5 plus 2 times 2. And then the next one, T of 4, is going to be equal to 5 plus 2 times 3. And then the next one after that, T of 5, the fifth term, is 5 plus 2 times 4. And when you write it like that, which you can see, you are consistently adding by 2, or your slope is basically equal to 2, we can now generalize what's our general equation. T of n is equal to 5, and then plus 2, which I'm going to go ahead and say is the difference, so it's a 2 right here, multiplied by n minus 1, where n is basically what term you're supposed to be on. So that's usually, the best way to come up with the equation. If you can write it as a pattern and you can see the equation, that's great. To generalize, an arithmetic sequence equation is going to be t of n is equal to, the 5 is really the first term, so that's t of 1, plus 2, which is supposed to be the difference, the number that you're adding in order to get from one term to the next, multiplied by n minus 1. So this is going to be our general equation for arithmetic sequence that we can go ahead and use from here on out. As for the geometric sequence, it is exactly the same idea. Well, let me go ahead and give you an example of a geometric sequence first. Maybe we can have the equation as the following. T of n, once again, is going to be equal to 3, comma 6, comma 12, comma 24, comma so on and so on and so on. Now, note what's happening here is just as we said, it's a sequence where you multiply consistently to get from one term to the next. And what I am multiplying by in order to get from one term to the next is 2, just for simplicity's sake. So if we were to generate a pattern just like before, we're going to go ahead and start by saying t of 1, the first term is 3. T of 2, the second term, is 3 times 2, which gives us a 6. T of 3 is equal to 3 times 2 squared, which is equal to 12. T of 4 is equal to 3 times 2 to the third power, which is 24 once again, and so on and so on and so on. But, as soon as you write these terms, as soon as you write out enough terms so you can see what's actually happening, and by the way, t of 1, I guess we can write that as 2 to the 0 power, and t of 2, we can write that as 3 times 2 to the first power. Now you can probably see what the equation is going to be. T of n, which is my equation in this case, is going to be 3 multiplied by 2 to the power of n minus 1 then, where n is supposed to be your term. And to put it all together, for our geometric sequence equation, our equation is going to be t of n is equal to the first term, because that's what 3 is in this case, multiplied by r, which we call for ratio, meaning the number you multiply in order to get from one term to the next, to the power of n minus 1. So let me take all these guys right here, let me drag this one down, right? And those are going to be the equations that we're going to be working with. So that first one right there, that's going to be the arithmetic sequence then. So arithmetic sequence equation, okay? And this is going to be our geometric sequence equation. And let me go ahead and get rid of this weird box that's just kind of in the way. All right, so here we go. Let's go ahead and take these for a test drive. Here's what I want to do now. Given t of n is a sequence, right? What I want to do is maybe predict a few terms. So the first one is not too bad. You're given the first term, we're given the second term, we're given the third term. We probably need the fourth term and also need the fifth term. Well, hopefully you can kind of see right off the bat, the pattern is I'm just really adding 5 each term. So t of 4, if I'm just adding 5 more to the next term, then that should be equal to 34. Whereas t of 5, adding 5 more to that previous term, that's going to be equal to 39. That's the easy part. Next, derive the equation for t of n. Well, if you recall, since you're adding consistently by 5 over here, adding consistently by 5 over here, and so on and so on and so on, we can say that this is really going to be an arithmetic sequence, which again, in turn, this is really just the linear equation then. So writing it term for term and, just side by side, we need the first term, we need the difference, and then we have n minus 1. Let me go ahead and write it over here. T of n is equal to the first term plus d multiplied by n minus 1. Well, we already said it. The first term is equal to 19. The difference is going to be 5, and then we have n minus 1. So there we go. That's going to be our equation, t of n then. Now, once we have the equation, everything is pretty much on smooth sailing. We can use that to solve for what we need. Use t of n to solve for the 31st term then. So that's what t of 31 means. So we're going to go ahead and replace n is equal to 31 into the equation and solve for what's t of 31. So t of 31 is equal to 19 plus 15 multiplied by 31 minus 1. Hopefully we can do this without a calculator. That's 19 plus 5 multiplied by, looks like 30. So it's equal to 19 plus 5 times 30. That's a total of 150. So the answer is going to be 169 then. So that's going to be your 31st term. And finally, the last one, going backwards. If you know the equation, I want to know what term, meaning I want to solve for what n is equal to, is the number 109. Well, 109 is supposed to be the result, so I'm going to go ahead and replace t of n with that then. So in our equation, again from part B, we're going to go ahead and say that 109 is now equal to 19 and then plus 5 times n minus 1. And we definitely should be able to solve for n over here. Running a little slow in space, so you're going to have to forgive me. First, we're going to subtract 19 from both sides. So 90 is equal to 5 times n minus 1. So divide by 5, that is equal to 18 is equal to n minus 1. So that means that n is equal to 19. So that means it's going to be the 19th term then. All right, so hopefully that was straightforward enough. Next, second to the last, the next one is, given that t of 1 is equal to 2000, t of 3 is equal to 500, and we know that this is a geometric sequence. So changing it up, instead of arithmetic, we're going to say geometric. I want to derive the equation and then use it to solve for the seventh term. In a way, this is really just what we did previously, except changing arithmetic for geometric. So I'd like to maybe solve for some of the knowns and unknown then. Now, I know t of 1 is equal to 200, or 2000. Then we don't know what t of 2 is, and then we know what t of 3 is, so that's going to be equal to 500. Well, what I need to do is, well, probably write down the geometric sequence equation just to help us out. T of n is equal to the first term multiplied by r to the n minus 1. If you think about what we have and what we can kind of like, substitute and all that stuff, we know the first term, that's 2000. That goes into there for t of 1. We know the third term, right? Right there, that's when t of 3, the third term, is equal to 500. That's when n is equal to 3. So if we were to put all of that into equation, here's what we can have. T of 3 is equal to t of 1 multiplied by r to the power of 3 minus 1, right? Replacing n with 3 and so forth. Well, t of 3, we just said we have is equal to 500. T of 1 is equal to 2000, and then multiply by r squared, because 3 minus 1 is equal to 2. So clean that up a little bit, divide everything by 2000, we get 1/4 is equal to r squared. And this part, you gotta be careful. We gotta solve for r, and there are actually two answers, believe it or not. R is equal to 1/2, or r is equal to -1/2. So what that means is there are actually two sequences with this setup. One sequence is t of n is equal to, remember, just going back to this equation, the first term, 2000, multiplied by 1/2 to the power of n minus 1. Whereas the other equation, which also satisfied this condition, is 2000 multiplied by -1/2 to the power of n minus 1. And depending on what you need to solve for, you're going to have to use the equation accordingly. Now, in our final part, it says, after we derive the equation, I want to use it to solve for the seventh term. Well, if you look at our two answers, right, there are possibly two answers because we have two equations. But if you look at n is equal to 7, I'm hoping you'll notice that it really doesn't matter which one we use it to solve for, because when n is equal to 7, we're going to have n minus 1 in the exponent, which will give us 6. And 1/2 to the 6th power, or -1/2 to the 6th power, they should yield the same thing. So if you don't mind, I'm going to go ahead and kind of erase a little bit of space just so that we have something to work with. And I'm going to go ahead and do like we said, which is go ahead and plug in n is equal to 7. And when you do, we are now going to have the following then. T of 7 is equal to 2000, and then multiply by 1/2 raised to the 7 minus 1. And like we said, that is going to give us an even number for the exponent. And so this we're going to keep as our answer. So we can either keep it like this, or I guess you can write 2000 and then divide it by 2 to the 6th. And 2 to the 6th, if my math doesn't suck, it's going to be equal to 24 then. And if I put it into this equation, I guarantee you that will give us the same thing. So that's the cool part. All right, so there we go. Hopefully you guys are okay with this. Let's see. The last one, which we can kind of talk about here, is how many multiples of 4s are there between the numbers 100 and 500 inclusive? Can you also find the sum of all of those numbers? Now, this one, once again, I want to leave for you guys to kind of discover a little bit on your own. But yeah, this is actually related to sequence and series, because here's what you're actually saying. Between the numbers 100 to 500, right, I want to know how many terms there are. So it starts with 100, 104, 108, 112, and so on and so on and so on, right? All the way to, I guess, where it's going to nearly end, 492, 496, and then finally 500. Well, I want to know how many terms there are, so can you maybe find a way to do so, recognizing that this sequence is what kind of a sequence? And now to take it even one step further, is there a way for you to sum up all these numbers cleverly, right? And I do believe the answer is yes, so I'm going to let you guys go ahead and discover that one. Okay. All right. Well, thank you so much for your time. Hope you have a good one, and I'll see you next